Welcome to yet another video where we're now doing the cross product. And before we get into it, I just want us to know what the learning outcomes are for this. So we're basically going to be calculating the cross of two vectors, obviously, and then determining the resultant vector direction. And then after that, the third one is calculating the area of a parallelogram and a triangle using the cross product. And then lastly, understanding when the cross product can and cannot be used. Right? In the previous chapter, we learned about the dot product and that the dot product basically produces a scalar or a single number or a constant, and the cross product, however, now produces another vector. So I wrote down some differences between the dot product and the cross product that you can see here on the screen. And in simple terms, the cross product is an operation between two 3D vectors, and it produces a new vector that is orthogonal or normal or perpendicular to both original vectors, right? So you can just read this if you want to, the difference between the dot product and the cross product, but I'm just going to move on to the next slide. So I think I wrote somewhat something that I just said here. But if we have vectors u and v, their cross product is this, right? And you read it as u cross v. So this cross, instead of now saying u dot v, you now say u or vector u cross v. And then you can obviously calculate, just like I said, with 3D vectors, you can calculate their cross products, but not with 2D vectors. So unlike dot product, where you can either do for 2D or 3D, cross product only works for 3D vectors. So for this, you obviously also have to know your determinants, how to calculate the determinants of a matrix for you to be able to do this. So I wrote down a formula for cross product, or actually I need us to work on it, but if u is this, u1, u2, u3, like I said, you have to know your 3D vectors in three-dimensional planes, and v is that, or v1, v2, and v3. The cross product is basically found by finding or using the determinant of the cross of v times u. And I just need you to also pay attention, not direction, but what you started with here really matters. So what you start with, in this case, it's v. So v is going to be in the second row, and u will be in the third row. Right? So if we started with u would be in the first row and v would be in the second row. Sorry, in the third row or whatever. But I think you do get what I'm saying. So order does matter. If they say v times u, you can now just switch to u times v, or finding the determinant in, vice versa. Here I wrote a 3D vector where you have I, j, and k, and the vectors, obviously, or whatever components that are in the vectors. And where I is the unit vector in the x direction, if you think of your planes, I is the unit vector in the x direction, j is a unit vector in your y direction, and then k is the unit vector in your z direction, right? Which is what I wrote here. And let's have an example or some calculations to work on. So if you're given u being 2, 3, 1, and vector v being 1, 4, 5, and you're asked to find the cross product between the two, what you want to do first is find the determinants of both. So you would obviously have to make your own determinant. Remember, you always have your I, j, and k, and then it just depends. If now we're talking about v crossed with u, we have to follow that, right? What you would have now in this case, because we're starting with v is 1, 4, 3, or 1, 4, 5 actually. So 1, 4, and 5. U is 2, 3, 1. So 2, 3, 1. Right? That is step 1. Step 2 is to expand expand across the first row for the I components. So like you would when you're finding determinants, you're going to close off this row where you have the I. Whatever you're left with is your new matrix that you have, and you would basically from there find the determinant. Right? So you would have, in this case, you're left with 4, 5, 3, 1. Actually, you have to be more specific how you write it. Okay, it's 4, 5, 3, 1. 4, 5, 3, 1. And then your I, you write it here on the side. This basically now is, if you were to find the determinants, you go 4 times 1 minus 3 times 5. So you would have 4 times 1 minus 3 times 5. Close that up, and you multiply it with the I component. Right? Calculating this, you would have 4 minus 15 I, or unit vector, which 4 minus 15, I think it's negative 11 I, right? And then secondly, we have to expand across the second row for the j component. So what you do is you come here, you go by where j is, and whatever that is within J, as in the columns and the rows, we don't want that. We want whatever that's left, and we're going to make a matrix out of that. So in this case, you have 1, 5, 2, 1. So you have 1, 5, 2, 1, see, and your J unit vector. And this would basically be 1 times 1 minus 5 times 2. So 1 times 1 minus 5 times 2. I would actually advise you to not really rush, even though you feel like you know your calculations. Just don't rush, because you might make mistakes like I just did. We actually have to have a negative here, because what you do is you go, don't have space, but you go plus minus plus, right, with determinants, and I didn't have that. So yeah, just be careful with your steps. So that's negative 1 minus 10 J, which gives us, so that would have been negative 9, and now you have 9J. And then lastly, you expand across the third row for the K component. So what you're going to have is, you basically find the new matrix. In this case, it's going to be 1, 4, 2, 3, right, along the K component. So you would have 1, 4, 2, and 3, K, or the unit vector of K. I think let me just start here. So that's going to be 3 times 1. So 3 multiplied by 1 minus 4 times 2, K. And this would be 3 minus 8, K. And that's negative 5K, right? And then step 3, which is the last step, is to write the vector in positional form and then the ordered form. So firstly, we have negative 11I, 9J, and negative 5K. So this would be positional vector form, but if obviously positional means starting from the origin. But if you just want to have it in ordered pair form, because we were given the vectors in ordered pair form, if you think about it, we were given U in ordered pair and V in an ordered pair form. So you would want your final answer to be somewhat like that. So now you would have negative 11, 9, and negative 5. Right? And this would be your final answer. And that's how you basically find your cross product using the determinant. Basically means the vector that's produced by, so if you have, in this case, we were doing V times U. So the vector that's produced by this is negative 11, 9, and negative 5, right? And this vector is always perpendicular to both U and V, right? So if you have, I don't know, I have examples, I think, at the bottom of how to find the perpendicular of both vectors. But basically, your cross product is the perpendicular vector to whatever vectors you are finding, right? So we use the product, the cross product, to actually find the vector that's perpendicular to two other vectors, and we also use it to find the areas and stuff like that, which we're going to get to in a second, or 15 seconds rather. So how to find the direction of a perpendicular vector? Obviously, if you have really found your answer like this, you would know. But just to analyze, let's work on this, right? So I'm just also going to have some other video here on my right to basically show you what I'm doing. So it's called the right-hand rule. And the direction of the cross product is determined by the right-hand rule. So whatever direction our perpendicular vector is going to look is determined by the right-hand rule. So you can obviously have a perpendicular thingy like this. But for us to know which direction it's going, like up or down, we have to know our right-hand rule. So what you do is you point your fingers in the direction of the first vector. In this case, our first vector is U, right? Because you're starting with U. So you point your fingers in the direction of that. Obviously, you have to use your right hand. And then you curl your fingers towards the second vector, so V. And then the thumb points in the direction of U times V. Right? So now that means our perpendicular vector, or the cross product of U and V, points in the negative direction. So it points down, right? Another example, if you have these two vectors, let's say you could have, a perpendicular line like that. Okay, and for us to know which direction it's facing, you're going to point your fingers in the direction of the first vector, which is V in this case, so V. And then what you do is curl your fingers towards the second vector, and then your thumb points in the direction of V times U, so it points upwards. And that's basically how you do your right-hand rule. So if they ask you to draw the vectors and then draw the cross product of the two vectors, in your mind, just also use your right-hand rule so that you know if you obviously have somewhat the correct answer. Let's talk about the reversing the order. So the cross product is not commutative, right? Which means that if you have u times v, that's not equal to v, sorry, crossed with u, not times, crossed with u, right? In fact, u crossed with v is equal to negative, and then you kind of do the commutative, but now with a negative, right? So it's going to point in the opposite direction. So this basically means changing the order changes the direction, but not the magnitude. So if your cross product was 5, right, pointing upwards, if you flip it or you kind of do the commutative but with a negative, it's going to be -5. So you don't really have to now calculate using the determinant again, but now with a negative and all of that. Just change your sign, right? If it was a negative, it would be a positive, and if it was a positive, it would be a negative. Now, because we're talking about the magnitudes, let's move on to magnitudes, right? So the magnitude of your cross products, the formula is the length of the first vector multiplied by the second vector and their angle, or you can say sin theta, right? So remember, with your dot product, you would use cosine. And now, because we're finding magnitude and not the dot product, you basically use sine. And there's a whole proof about this and how it's derived. You obviously have to know your, let's say you have u crossed with v squared, right? So if you remember, actually dotted with, I think it's dotted, kind of don't remember. But if you have something like this, and there's just a whole proof about it, and how you move from cosine to sine, and that's because now you have 1 minus cosine squared theta, and that's equal to sine. And yeah, there's just a whole lot of things that you might have to do to prove this. I would say know your proofs, every proof. Make sure that you know all the proofs, because you never know what they might ask or what they might change in, like compared to previous papers. Another way to do this is, if you think of your unit vectors, a unit vector is equal to the vectors. In this case, it's the cross product of the vector. So whatever resultant vector that you get, and the magnitude of that cross product, you would have a unit vector or a vector that's parallel to whatever vector you had, right? And you can manipulate it like this if you want to. But if you're finding the direction, you don't have to have multiplied by the unit vector, for example, here. And then your area of a parallelogram or a palm and area of a triangle is dependent on this magnitude. The magnitude is dependent on that. Okay, area of a palm is equal to the magnitude of a cross product, or the extended version of that. Obviously, if you have angles and you want to find the area, you can just use this formula. And for a triangle, it's quite similar to that. You just have to half it or divide by 2, and you would have an area of a triangle. So that's just it. Sometimes they can ask you to find the two unit vectors that that are orthogonal, maybe to, let me see, I'm trying to make a question in my head. So find maybe two unit vectors that are orthogonal to maybe the vector u and v. What you would want to do is, let's go up a little. Let's say they say to you, find the unit vector that's orthogonal to v and u. What you would do is find the cross product of that. And then from there, if you can, take out a common vector. And then you would have one unit vector. And then from there, obviously you also have to find like the direction, or sorry, the magnitude. And from there, you can just, if you're flipping it, you would have the negative one or the positive one, it just depends. And both of them would be unit vectors that are orthogonal to whatever vectors you were dealing with in first place. I hope you do understand. Sometimes you could have just this, and then they ask you to find the two cross products that are orthogonal to v and u. What you would do is find this, and you'd be like, oh, good. And then the other one would be the negative one when you're flipping the direction. So if you think of it, if you have, okay, if you have, let's say, these two vectors, and you have maybe this orthogonal going up, the other orthogonal vector would be maybe another one going down like that, right? Which has the same magnitude, just different directions. So you would multiply this by a negative, and then multiply in. So this would be 11 minus 9 and 5, right? So I just hope you do understand what I'm saying. Underneath or down here at the end, I have some practice questions that I would like for you guys to try. Right, so these are the practice questions. Firstly, find the cross product of these two vectors. Secondly, calculate the area of a parallelogram formed by these two vectors. You can draw it if you want to, just for good visual representation. And then I would like to also make you find the area of a triangle formed by these two. and then show that the vectors this and this are parallel by using their cross products. Then I have here note that vectors that are parallel have a cross product that is equal to 0. It's not the same with your dot product, where if you're dotting the two and they're giving you 0, that means they're orthogonal. So catch the difference. And yeah, I think that's it. Just don't forget, if you're finding the determinant, you have plus I, negative j, and plus k, right? Remember that formula. Remember how to find your cross product and how it's different to the dot product, where in dot product you have your cosine theta, and here you have your sine theta. With your cross product, you're basically finding things like your area of a triangle, area of a parallelogram, and also orthogonality in depth. And then with your dot product, you're basically learning how to find your area. Sorry, not area. Actually, you're learning how to find things like your, I forgot this, your angles. So you obviously have to know the inverse maybe of cosine to find an angle, things like that. And yeah, a little bit on the orthogonality, but mainly orthogonality is found using the cross product. And that's it for me. Thank you guys for subscribing, showing love, and liking. Thank you so, so, so much.